Great. Okay, so now it's Wenjie Fang from the University Gustave Eiffel, and he's going to talk about the maximal number of subword occurrences in a word. Thanks.
Thank you, Cecile, for the introduction, and I'm very happy to be able to talk to you here about my research. And in fact, in this talk, I more want to tell you it's more like a story of a very hard open problem that I try to work on. I get some results, but the results are, well, okay, not that, it's quite good, but it's okay. But the most important part is the open problem. And it's about words. So words, as we all know, is just a finite sequence of symbols from a finite alphabet. And when we have a structure like this, we are interested in their substructures. And in the study of words, we usually look at two kinds of substructures. One is subwords, which is essentially we pick a subset of positions in the word that we call the occurrence. And then we look at the letters at these positions, we pick them up, and we have a smaller word, and it is a subword of the original word. Okay, but there is another notion of substructure that's called factor. That's essentially we require the subword to be of consecutive positions. Okay, for example, if we look at the word zero, oh, we don't have the pointer. Oh, yeah, yes. 011001. In fact, we can see that 0 occurs 5 times as a subword because for the first 0, we have 3 ones after it. And for the second and the third, we only have 1 1. So it's 5 times. But if we count factors, we tell them to be consecutive, then there will be only twice as occurrence. In general, counting problems on occurrences are easier for factors than for subwords because factors, they're consecutive. So we have much more restrictions on it. So that's why in this talk, we're only talking about subwords. And we're going to look at the occurrences, which is the number of subsets of positions. And we denote it either by like this, like a function occurrences of U in W, or there is also another more elegant notion, notation, which is the binomial notation like this. Okay, and this is a very natural and very well-studied notion of substructures. And of course, there has been a lot of research in various directions about this kind of number of occurrences. And I just cite one that's the familiar for our community. That's the one done by Flageolet, Stankowski, and Valet in 2006. They look at a fixed subword, U, and then they look at the number of its occurrences in a very large, very long random word. And they show that when the length of the word, of the long word, tends to infinity, then with some rescaling, the number of occurrences of a fixed subword will have a normal distribution. Okay, and then they also obtain some large deviation results out of it. And that's very nice. So in some sense, it's something that we should expect because we say that, well, we look at 2 different occurrences, they probably don't interfere much with each other. So we should expect some kind of normal distribution. But it's not, the analysis is not that easy in the sense that because when we have an occurrence, then in fact we would fix some of the letters in the word. And when the subword has some self-correlation, then it will alter the probability that we have another occurrence of it. So in fact, in the rescaling and in the normal distribution, there would be some factor, etc., that is related to self-correlation of the subword. And it's usually the difficulty in the analysis here is from those self-correlations. And of course, this is like an average behavior, and we can also look at the extremal behaviors. For example, if we say that the number of occurrences should be 0, then we're in the domain of pattern avoiding words, which has been very well studied. And in this talk, I'm going to look at the other extremal, which is the maximum number of subword occurrences. And this comes, in fact, from a very natural algorithmic problem that one of the colleagues in my lab worked on a bit, at least. That is, given a word, what is the subword that occurs most frequently in the word? Can we compute it explicitly? And why we're interested in this kind of stuff? Because first, this is a very natural problem. We take a word, which is the subword is most frequent, it's very natural. And second, it's also related to some of the works in data mining, because in this community, they want to, well, given a database or some, well, we can see a word as a database, then they want to know which are the patterns that occurs frequently in this database, so in this word. So it's related to some of their research. However, this problem looks really innocent, but it's really difficult in the sense that we don't know its complexity. We don't know any algorithm in polynomial time that computes the most frequent subword, but we cannot, anyway, we don't have a proof that it's NP complete. So we have no idea about the complexity of this problem. And that means there is something that we don't really understand, well, after all these years of research, the subword occurrences in the word. So that's why I'm interested in this. Yes, please. No, it's not fixed. The length is not fixed. Of the subword is not fixed. So any subword of any length, we want to maximize it. Okay.
One character, you take the multiply the character. I'm confused.
Yes.
Oh, with fine. Thank you.
Okay.
Okay.
Not a problem. Now, the day, well, it's the first day. It's normal that we are a bit slow. Maybe. So that's why I'm interested in this problem. And then, well, what I'm going to look at is like I'm going to study a numerative version of it. And then we defined a function that's called max occurrences, which counts simply the number of occurrences for the subword that maximizes this occurrence. Okay, and then I'll define the subword entropy of the word, which to be simply the log of the maximal occurrences of base 2, log of base 2. Why? Because we see that an occurrence in the word is simply a subset of positions, so it's like a position, do we take it or not? So it should be our base 2. And if we look at this function, we want to consider its extremos. And we see that it's very easy to maximize this quantity. We just take the word composed with only one letter. And then, of course, the most frequent subword would be the word of length n over 2, if it was of length n. And then we can compute the subword occurrences. It's just a binomial. And then the subword entropy, taking a log out of it, it would be just n plus something, minus something, more like. So it's easy to maximize. Then we will tackle the difficult problem is try to minimize this quantity. And that's why we are interested in the minimal subword entropy that we defined like here, min as a subword of k, because this depends, of course, on the size of the alphabet. And that is for the length n. So this is simply, we try to minimize it. Yes? Without loss of generality, the alphabet itself, it's not important. It's only the size of the alphabet that is important.
Pattern is what? Regular expression?
No, pattern for us here would be subwords. So subwords would be, pardon? Subwords, I will maximize over all possible subwords here.
Oh.
I'll take them. Subsequence, yes, subsequence. It's scatter. It's it can be not at the. Yeah, it's W. Yeah, it's W. Sorry, this should be W. I minimize for the word itself.
W does not have any length here. U is of length n.
No, sorry, this should be a W. This should be W, sorry. That's because I was also completely confused when I wrote this. Sorry. Okay, so I want to study this, and this would be the minimal subword entropy. This would be the key. Well, this would be the object that we are really interested in. So first, we want to study it. Well, the first step is we try to give bounds on it. Well, we have some trivial upper bound. Well, we just take the example we took, the upper bound for the value of, for the subword entropy of any word will serve as an upper bound. So I take the most simple one, it gives an upper bound of n minus something, okay? And we can also do a relatively easy lower bound out of it. How do we do that? We fix any word W of length n, and then we take a random subword U of length alpha n. So now we'll try to tweak the length of alpha. And because the word we took was random, uniformly random, then the expectation of the number of occurrences would be very easy to compute. It would be just the number of possible positions, possible subsets, and then the probability that in this subset, we really have the word with the subword. And then we just take the log. This will be, of course, a lower bound on the subword entropy, because the subword entropy is something that's maximizing. So then afterwards, it's easy. We do a Stirling approximation, and then we try to maximize this function with respect to alpha, and it's maximized at alpha equals to 1 over k plus 1. And the value it gives is simply this on the right-hand side here. And because this bound works for all the words W, so of course it works for the word that gets the minimal subword entropy, so it's good. It's a lower bound. Okay, so these are the upper and lower bound of it. And then, well, we can also look at a bit of its properties. And in fact, it has a very nice property that it's super additive. In the sense that if we take the subword entropy for words of length n plus m, then it's larger than the sum of subword entropy for length n plus that of length m. The proof is not very difficult, but we need to pay attention to the small twists in it, because we are always in a, well, we are maximizing and then minimizing, things like this. So we need to pay a bit of attention, but it's very doable. And when we say that it's super additive by Pythagoras' lemma, it says that if we divide the minimal subword entropy of length n by n, then it would tend to some limit, which can be infinite, but because we have already upper and lower bound of order, linear order out of it, so we know that the limit would exist, and from the upper and lower bound, we know that the limits will be bounded by these two quantities. Okay, but we say that, wow, this is not very good bounds. For example, the lower bound, the gap between lower bound and upper bound is not negligible. And the upper bound, of course, is very stupid, because we take the subword entropy that's the largest. So it's a very stupid upper bound. So the idea is that, can we get a better bound out of it? The problem is that we have no idea, because the problem is so hard. So when we have no idea, what do we do? I don't know what do you do, but I will first compute the first terms, the first words of small lengths that maximizes their subword entropy. However, the problem is that it's very hard, because we have so many words. It's exponential. On a computer, even on a computer, it's not that easy. So on the experiment, we started with the binary case. So we have the alphabet, there's 0, 1. And we see that, well, at least for the first words, for words of length quite small, that minimize the subword entropy of its length, well, we see that it's as if there is already some kind of structure out of it. Okay, it looks kind of regular. And if we look at the symmetries of these words, many of them are either palindromic or anti-palindromic. So P is for palindromic and A for anti-palindromic. So this looks very promising. So maybe there will be still some structures in these words with which we can get a better upper bound out of it.
Are these unique minimized up to changing 0 to 1 and 1 to 0?
Yes. Why? Because, yeah, was the case here. However, well, of course, we try to further our experiments. The problem is that, well, we used to see some structure, and now we don't see it anymore. I don't know if you see anything from it, but at least I don't see a lot of things from it. And at least we can observe that the symmetries, there are a lot less symmetries in it. So maybe symmetry is not really a story for these words minimizing the subword entropy. So I was a bit confused, and sometimes you can also observe that for some lengths, particular lengths, there would be several words minimizing the subword entropy. Well, even counting the trivial symmetries, exchanging 0, 1, or flipping the word altogether. And sometimes there will be one word without symmetry and the other with some symmetry. So it's more and more confusing the more and more we do experiments. Anti-palindromic and palindromic. Well, when it's long, it's difficult to see it's palindromic or not. Anyway, we are confused. So we decided to give it a last push to see what are the really long words that minimize the subword entropy. And here's the result. Well, it took some time to compute. And for example, the last line for the size 35, it took 11 days on our server, on a single core on our server. So it's a small computation, of course. And it's not trivial to do that, because if we do it naively, then the complexity would be 4 to the power of n, and this is not really doable on modern computers. But if we take some efforts on optimization, then we can do that. And already from this last part of simulation, we see that, well, at least we see that we don't have symmetry anymore. There's nothing. So we're probably sure that symmetry is not the story for this subword entropy. And then, but there are still some structures. For example, if we look at the runs, so consecutive letters in these words, we see that they mostly of length 1, 2, or 3. Sometimes we have some runs of length 4, for example, here, but it's relatively rare. And if we just pick a random word, it would not occur in so few times. So we can consider this as a structure. And we also see that if we look at the growth rate of the maximal occurrences, it's really relatively close to 1.5, which is the one given by the lower bound. But it stands slightly larger, solidly slightly larger than 1.5. So maybe the lower bound is not so tight. Okay. Now our idea is that we want to give better upper bound for it, for the minimal subword entropy. And the idea is to find the words that looks like this, looks like what we get, but somehow analyzable. And what are the words that looks like them? Well, they will be words of run length 1, 2, and 3. And for them to be analyzable, we better hope them to be periodic. So the natural candidate would be the words of run length 1 or 2 or 3, which are periodic. So the 3 candidates we have are of period 0, 1 or 0, 0, 1, 1, and then 3, 0, 3, 1s. And for these 3 candidates, we have some miracles happening, because remember that this subword entropy problem comes from the algorithmic problem of finding subwords that occurs most frequently. And in general, we don't know how to compute them. However, for these 3 candidates, we have the following results saying that for these words, at least there will be a most frequent subword that are also periodic, and we know their form. We don't know how their other most frequent subwords look like, but at least we have these, at least have these words on which we can analyze. So for 0, 1, the period of subword would be 0, 1, and the same for 0, 0, 1, 1. And then for 3, 0, 3, 1s, the period of the most frequent subword will be 0, 0, 1, 1. Okay, and this is done using some local analysis on the subword. And this is the key results because, well, we also want to do the analysis on other periodic words, but, well, experimentally that works. Periodic words usually have periodic most frequent subwords, but we have trouble proving that this is indeed the case. And it's one of the conjecture that we have. And then, once we know what the most frequent subword looks like, then it's totally in the realm of enumerator combinatorics. We can do it with analytic combinatorics. We know that, and it's not very difficult. First, we write the generating function for the occurrences of periodic subwords in periodic words. So the period of the subword denoted by U, the period of the word denoted by W. And then we use the variable X for the repetition of the word and Y for the repetition of subword. And then we do some computation because we can write recurrences on the number of occurrences of these periodic words. And we obtain that they are, in fact, all rational functions and of quite simple form. Okay. And then once we know that they have simple forms like this, combining the result, that we know the most frequent subwords, at least one of them will look like a periodic word. Then to compute the maximal occurrence of the periodic word in these three families, we only need to take, for example, the coefficient of x to the power of m. Then it will be a polynomial in y, and then we pick the largest coefficient in this polynomial, and then we have the maximal occurrence. And this is something that we can do very easily in analytic combinatorics. And in fact, this is not a coincidence that they are all rational functions because this holds, in fact, for any word and any periodic word and any periodic subwords. The problem is that we don't have the results that the result like this, that the most frequent subword of a periodic word is also a periodic word that we know. So we cannot directly apply this to obtain upper bounds. Okay, now afterwards, the computation is easy, and here are the results. The first two lines are in fact quite easy because they are just binomials with some exponential factors. So we can just simply maximize them using Stirling's approximation. The last one is more complicated, but still we are within the realm of rational functions. We just want to maximize in some direction. So either we do automatic analytic combinatorics in several variables, which has been done in SageMath. We just put the rational function in it, and then it spit out the results automatically. Or in this case, because the generating function here is still relatively simple, so we can do with set point estimation on large powers. And that's what we obtain. We know that the direction that maximizes the number of occurrences would be R equals to alpha m, with alpha a number is really close to 2/3, but it's not. It's the solution of this equation of degree 4. And then the subword entropy would be m times gamma, with gamma given by this a bit complicated expression, which comes from the maximization of the coefficients. And then this result gives us an upper bound on L2 because we are in the binary case. And then numerically, the three families gives these three numbers, and we see that in fact the second one is the best. So what we get at the end is that we have a bound of L2 between the lower bound from random subwords and the upper bound from the family of periodic words 0, 0, 1, 1. And we see that, well, at least they are much closer now together. Okay. But of course, a lot is still unanswered. For example, can we get the value of L2? like this. I don't think it's within reach for the moment, but maybe you have better ideas. But even if we don't know its value, can we give better bounds by analyzing other families of words? Or can we tell something on alphabets of other sizes? And that's still very open. And then we also have the question, the problem that I already mentioned, that we observe experimentally that periodic words will mostly have periodic subwords that are the most frequent subwords. Can we at least prove this so that we can use the universal result on the periodic on the subword occurrences function of generating function of periodic words and subwords to have better bounds, to get better bounds for L2 or other things? If it would be, even if we cannot do it for periodic subword, but if we can do it for quasi-periodic subwords, then we will already be able to get some bounds out of it. Okay, and then we'll say also that maybe it's too difficult to study the words really minimizing the subword entropy. Maybe we relax it a bit. It will give us some more structure to analyze, etc. And maybe asymptotically, even if we cannot get the really minimal number, maybe we can get asymptotically a better bound for L2, for example. However, these problems are quite difficult because of the structure, because we are, in fact, minimizing some maximal value, because the subword entropy is that we maximize the number of occurrences, and we want to minimize this quantity. So the problem itself has a difficult structure, and we can also see that in the experimental data that is really chaotic. And even some very intuitive ideas, intuitive phenomena, we cannot prove it. For example, here are two questions I listed here, but there are more in my archive paper. First is the subword entropy per letter, minimal subword entropy per letter is ultimately increasing. Intuitively, it should, because if it's not ultimately increasing, it means that there will be some resonance due to the length of the word. But that's really difficult to imagine. And the second is that for any word, there will be all of its most frequent subwords of length less than 1/2. It should be, because if it's no use to have a subword that's of length more than 1/2, we don't have as much possibility for the positions. It's much harder to be a subword with more letters. However, we cannot really prove it, even for this very simple case. So if you have any ideas or questions concerning these problems, I will be very happy to hear about them in the conference. Thank you very much for your attention.
Are there any questions? Daniel, I'm running to you.
Thank you. So you had the complexity of 4 to the n for your experimental algorithms.
Yes, but yeah,
up to 35. So that makes roughly 10 to the 23rd operations. So what kind of optimizations did you do to manage that?
First, the 4 to the n is really naive. So if we are less naive, then of course we can improve already a lot. But in fact, for the real optimization, I use the minimal and maximal structure to preemptively eliminate a lot of possibilities already. So like when I analyze a word, I try to find a subword that probably occurs very frequently in it, and then I just compute it once to eliminate this word. Yes, it's like a branch and bound. Yes.
Cyril?
Okay, so for me, there are several problems which are a little bit reminiscent of this one. So there is, for example, the longest increasing subsequence in permutations, in which there is also this flavor of non-cumulative stuff, and for which the naive algorithm will be exponential. But luckily, we have this jeu de taquin approach or dynamic programming, which allows to be linear time or something like this.
Yes.
Did you try to consider some type of jeu de taquin for this problem? If there could be one, or is it already existing somewhere?
I don't think that this exists really, because I did some research in literature, and in fact it's not that well studied. But I don't think that that would be some kind of jeu de taquin operation, because it's subword, and then the word can wait. The occurrence of subword can be far from each other. The letters can be far from each other, and in the jeu de taquin, it's often not that easy to, well, the consecutivity plays a role in jeu de taquin.
Yes, and the other problem will be the De Bruijn sequences, which
Yes.
is for sure similar to this problem, but when it is consecutive factors.
Yes.
So is it already considered about these names? If we want to Google search this problem, is there a canonical name for it?
That's a very good question, and I don't have an answer. I didn't do that in that direction, because I said to myself that factors should be much easier to do, and then I didn't research in this direction.
Conrado has a question.
Yes, I'm curious about, is there something in between factors and subwords, like you allow some amount of distance between the different letters, but not any amount, like in a subword. Therefore, you would have more constraints, and things would be easier from the algorithmic and the analytical point of view.
Yes, indeed, there is also some notion of generalized pattern. It's like mesh pattern in permutations that we can allow. Well, we force some letters to be consecutive, but others not. Indeed, but algorithmically, I think it would make the problem more difficult, because we always have the possibility that some of the letters can be non-consecutive. So it's, in fact, it's the non-consecutive part that makes the problem complicated. So once we allow non-consecutive letters, then it will be complicated. Yes, please.
Okay. So, of course, all your work here is with deterministic sequences, and you want to optimize. But I also noticed that your example, they look...
They were not.
Take a random binary sequence and see what is the maximum number of a subword, and compare them and see how much your results differ from that.
I would say that I didn't see research in the literature in this direction, and indeed, this is also a very natural question. What I did is that I did some computation on the histogram of the maximal subword occurrences of words of a given length, and in fact, we can see that there is a concentration in the middle. And the maximal occurrences is like in the extremal, is a bit far away in the extremal. So we can still see something, but I'm not sure if that answers your question. But we can still see something, and it's very natural to try to go further on it. Thank you very much.
I think questions are not allowed from the back of the room. Sorry, I'm joking. Any more questions? Okay. Yeah.
Thank you. So you tried runs of size 1, 2, and 3 to find an optimized minimum here.
Yes.
Have you tried other lengths? Because indeed, up to size 35, we do not find a lot of other lengths of run, but maybe because they appear a lot later.
Mm-hmm. Well, I would say that with the numerical results, we see this is for run length 1, run length 2, run length 3. We see that it's like optimized for, well, it's minimized at 2. So I think for myself, well, maybe we don't need to continue.
Okay, thank you.
And another idea is to mix the periods, but that makes the analysis a bit difficult, and that's why I wanted to show this result. Does periodic word have quasi-periodic most frequent subword? so that I can compute on this mixed length periodic words.
I know there are more questions, but I suggest we keep them for the lunch break. So thanks a lot, Wenjie, for the talk.